Sergey is a postdoc in us group, and he is working on several topics from the chat we had. One of them is system identification for temporal networks, who he will present us.
Thank you for the introduction. First of all, I'd like to say that this is a joint work with my supervisor, Professor Piet van Nichem. And as I told you, the problem is on temporal networks. So here is the outline of my talk, but I will start with the problem statement. So the main difference is that if we consider real networks, we observe that they are not static and they evolve over time. You can think about human mobility and our daily interactions. So what we actually observe is we observe our interactions at different timestamps, like the day 1, day 2, day 3, day 4. And I mean, the connections are different. So the question here is that based on the interactions, can we say something about the process? Or can we define the process that actually generates me this sequence? Here, I would like to point out that we don't do any prediction. So we want to find the process which generates this specific sequence. But if this process is good enough, right, we can actually do it also for some T-step prediction. So for this problem, we wanted to start whether we can find the process, whether we can define it as the linear process. And we consider the problem from the system identification approach. So I'm not sure that whether you are familiar with this system identification. So that's why I have this slide about the system identification and the classical model. So the general idea is that you have the system and you observe some measurements, which are the inputs and the outputs. So numbers, they correspond to different timestamps, like day 1, day 2, day 3, and so on. So the output and input can be several measurements. So these are like multi-dimensional vectors. And there are like some measurements of the system. So the question is, can you connect these inputs and the outputs? Can you find the model which actually do, in some sense, this approximation of like the prediction? Actually, in the field of system identification, there is a linear time invariant state model. So the most important of this is that this model is linear. And the general idea is that we have the system and it has the internal state. And in fact, we can define the dimension of this internal state. And the general idea is that the output can be represented as a linear combination of the input and the state of the system. But at the same time, since I mean, all these measurements, they evolve over time, at each timestamp, we actually update the state of the vector. And in fact, we can actually represent it in this equation. So this is a general model, and what is good is that this field of system identification is well developed, and there are models which find such matrices A, B, C, and D, or I used indentation Q here, and they actually tell you what is the dimension of the state vector and what should be the values, the initial value of the vector. So you can actually get a really good approximation of the output. And like one of the models is like the Fawcett algorithm. I will not describe it, but the general idea is that we can rewrite this equation and we can represent it as the matrix of the outputs, the matrix of the inputs, and you can use some properties of subspaces such that output can be actually expressed as a linear combination of these subspaces. So there is a model, so we can actually apply it to our problem. But now the question is how we can apply it to the temporal graphs. So what are the inputs? What are the outputs, right? And here I should say something about how we represent these temporal networks. So as I told you, we have this set of observations, And what we do actually, we represent each graph as a vector. We just store information about links in the graph at particular timestamp, right? So for instance, blue colors correspond that there is a link between certain nodes, and like zero, like this white spaces, like there is no link between them. So what we can actually do here is that if we use this vector representation, we can apply this subspace model and find this matrix Q and the initial state. Right, I have like the set of input measurements, like the graph at the previous timestamp, and I know the next graph, and this is also the vector. So if I have this set of observations, like t-1 graphs are the inputs and t-1 graphs are the output, I can actually use this, for instance, N4-CT algorithm to define those matrices, and actually I can do this one-step prediction, right? And I can do it like a linear model. However, this is not the aim of our research. So we want to generate not only the next graph, but we want to generate the whole sequence. And here we actually do the assumption that if these matrices are good enough, since this is my approximation of the graph at the next timestamp, and then I use the real one as input, I can use, if these graphs are quite similar to each other, I can use it as the input for the next timestamp. So this is, I think, like one of the obvious ideas what we can do here. So we modify the model. So suppose I know matrix Q and the initial state vector. So in fact, if I learn these matrices from my observations, then I just need to take the first graph and then apply these matrices many times and get the whole sequence of the graphs. What's important here is that, in fact, if you rewrite all the equations, you will have this power of the matrix Q because you do it like many times. And actually, this is one of the limitations because it's also about the properties of this of eigenvalues of this matrix Q. And in fact, not all sequences of graphs can be modeled with this model. In fact, we have proved that if the sequence is periodic, we can do such, we can apply such model, and it can get us accurate predictions. So I can actually talk about it. Here, one important thing is that to measure how good what is the performance of my model, I use the mean square error, right? I just compare the real vector sequence and the vector sequence which I get from the model. And again, we started from periodic sequences. And well, what is periodic? It's actually like the sequences which repeats after certain timestamps, right? You can also think about our daily interaction. We have some periodic patterns. And here, this is like an example. And if I divide these metrics into 3 parts, you may actually see that those areas are exactly the same, right? We know that the world is not exactly periodic, but still, I mean, we do this assumption, and we can actually prove that such periodic sequences can be modeled with this system identification, with this linear model. So in fact, why can we prove it? The first of all is that when we talk about this equation, we have matrix Q which we have to define, and we also have the initial state vector. And the powerful thing here is that we can choose any dimension for the state vector. So it's more of the question is how many dimensions we need. And this is actually why we can model periodic sequences. And in fact, since we assume that all vectors, all graphs, they repeat after certain periods, we can rewrite the initial equation in this form. And in fact, we have proved that if you look at this equation, you can actually see p vectors here and p vectors here. P is like the period of the sequence. And if I make this sequence of vectors linear independent, I can just use linear algebra and just move this set of vectors to the left part, and I can solve the equation for Q. But in fact, so it actually means that if I map all the vectors into p-dimensional space, I can actually find the matrix Q and do this kind of modeling very accurately. But in fact, P is like the upper bound, and we actually also proved that for some graph sequences, we don't need these P dimensions, and we can do less. And in fact, it's all about the rank of the matrix, which corresponds to the sequence of graphs. And actually, this idea is the basis for the algorithm that we propose, which actually do this modeling of periodic sequences. So so we know that in real life, the sequences are not perfectly periodic. What can we do here? And here we actually we introduce another model, but it is actually based on the idea that how many processes in real life are not periodic, but they're quasi-periodic. Like we have daily interactions, we all go to work a certain period of time, we go home, we do some certain activities. So what can we do here is that if we have the sequence, we can try to identify those periodic events which we observe in this graph sequence. So the idea here comes from the idea of the Fourier analysis, but this is actually called like periodic transformation. And in fact, the initial sequence can be represented as a set of periodic sequences, periodic events. To give you an example, what do I mean here? Imagine that we have only one link, and we know how it evolves over time. So suppose it is actually weighted. But if you look at this sequence, you can also see that it looks like periodic, but this is not exactly periodic. And what we can do here, that if we know the exact period, we can actually divide it into some sub-windows, and we can actually find the general pattern, like our average behavior during the day or something like that. And if we do this, we can approximate the initial sequence using this average pattern. And well, this is not exactly the same what we wanted, but it looks more or less similar. So what we can do actually, we can actually do this abstraction, like compute the difference between these sequences, and again work with these residuals. So this is the idea, like if we do it like sequentially many times, we can actually observe some sequential periodic patterns which we observe, I mean, in our graph sequence, I mean, in real data. So that's the idea. So this is the example that how to identify periods from real data. This is actually the real data about communications of students at school. We see that there is some certain points, right, when we have this decrease of the loss, and we can actually see that this might be a good indicator that this is actually the true period which we observe from the data. To conclude, I would like to say that we have tested this idea to artificial sequences, which are quasi-periodic. Like I generated like a simple periodic sequence, and then I made some noise. And I see that the more periodic sequences I use to explain the initial sequence, which is to the left, the more accurate it becomes. But I mean, for artificial sequences, this is not that fascinating, but what we also did is we considered some real data, which is available in the internet. So again, this is the connections of people at school in French school. And this is information about the total number of connections. But even from this information, you can also see that it looks like periodic because we have these patterns, right? And this is actually like 2-day data, so that's why some events are quite similar. And what we can do here is our first observation is that if we try to approximate the initial sequence as the sum of these periodic sequences, we actually tested 2 models. The first one is when I just use these periodic sequences, but the next one is when I do rounding, because in my data, it's a binary data, like whether we had a connection at certain time or didn't have it. So what we can actually see is that if we do this rounding at the final step, our mean square error, it decreases exponentially. So this is actually on the log scale, the decrease of the loss. But you can also see the absolute value here. And even you can see here that after 11 sequences, the model with rounded gives you the accurate sequence. So I think that's it. So we see that we don't need so much periodic sequences to model real data, the observed sequences. So as a result, we have modeled periodic sequences as a linear process using this idea from system identification for non-periodic sequences. We try to represent it in terms of several periodic events. And to conclude, like this is still ongoing research, and we try to find what is the best period here and how good are these periods for doing this type of prediction. So this is still ongoing. So if you have any comments or questions, I will be very happy to hear. Thank you.